Hello everyone. Today we'll be discussing on the topic convex hull algorithm. Yeah. So previously we were done with the number theory based algorithms, right? So from today, let's discuss the geometry based algorithms. The first one we will be discussing on is convex hull algorithm. So let's see what the definition part say here. The convex hull of a set of points is the smallest convex polygon that contains all the points. In simpler terms, imagine stretching a rubber band around the outermost points. The shape it takes is the convex hull. Yeah, simple one. Yep, let's see the explanation part. Let's see what the explanation part say here. Let's get into the explanation part here, right? Convex hull algorithm find this boundary basically among a set of points in a 2D plane. Among set of points in a 2D plane, right? So there are multiple algorithms to do this actually. We have Graham scan and Jarvis merge, right? Gift wrapping, also known as gift wrapping, right? Or the most common actually. Here, what we will do, we will implement Graham scan which works efficiently in peak of n log n time. So we'll be making use of the Graham scan. So you can expect that we'll be basically writing the algorithm based on the Graham scan, right? So steps of Graham scan here, we'll find the lowest point, nothing but we'll go with the lowest point, which is called as the pivot actually, which we will consider as the pivot, the point with the lowest y coordinate and lowest x if there is a tie. If there is a tie, we'll be going with the lowest x as well. Yeah. So we'll sort all other points by the polar angle they make with the pivot. Polar angle they make with the pivot. Just remember this. Next, what we will do after sorting, then we will traverse. First thing, we'll find the lowest point, nothing but the pivot. So then we will sort all the other points. The third point here would be we'll traverse the sorted list. After sorting, we'll traverse the sorted list and maintain a stack to determine whether moving from the previous points to the current points this one makes a left turn or the right turn. Simple. Yeah. If the right turn occurs, so there are two things. One we have to take care of here is one is left turn and the right turn. If the right turn occurs, then we have to pop the last point. Yeah. So it cannot be part of the convex hull. If a right turn occurs, we have to pop the last coin because it cannot be a part of the convex hull, right? So continue until all the points are processed. The stack now contains the convex hull. So exact same thing from the first point here, from the lowest, finding the lowest point until, so this one, the stack now contain and this one convex hull, the same thing, exact same thing will be articulating in the form of code, right? So let's start writing the algorithm, right? So first, let me import math here, right? So this is fine. The next step is so let's define the function to find the orientation. Orientation in the sense 0 is nothing but the collinear, 1 is nothing but the clockwise, and 2 is nothing but the counterclockwise, right? So I'll just go with def orientation. Yep, so this is fine. I'll just go with p, q as well as the r. Right, so next this one, what do we call, within the orientation function, so let me assign value to q of 1, so this is fine, minus p of 1, so this is also fine. Yep, p of 1 into, so this is fine, r of 0, minus q of 0, this is also fine, minus, so I'll just go with here q of 0, q of 0. So I'll just go with minus p of 0 as well, minus p of 0 as well. Next, let's go with a into r of 1 minus q of 1, right? Minus q of 1. Somewhere I have done something wrong, man. Just give me a second here. P of 1 is fine. Into r of 0 minus this one minus q of 0 is also fine. Yeah. So here, let me remove this one. Q of 0, let me close this one. Let me close the parenthesis here actually. Yep. So now this is fine. Uh, I had misplaced the braces actually. This is fine. Let's move on with the further things. Suppose if value equals 0, then what we'll do, we'll just return 0. Then we will just return 0. Yep, so this is fine. Else what we'll do, we'll return 1 if value is greater than 0, else we will return 2. Yep, so this is fine. So this is it for the orientation, this one function actually. Next, let's move on with another function named distance. So distance, because we have to write the function to compute the distance, right? So we have to calculate the distance. Basically, it is used for sorting, right? So let me go with def here, dist p1 comma p2. So within this particular function or the helper method, so I'll just return here p1 of 0 minus p2 of 0. This is also fine. Mm, to the power of 2 plus this one p1 of 1 actually minus p2 of 1. So this is also fine to the power of 2. Yep. Next, let's do one thing. Let's move on with the next step. So let's move on with the main convex hull function, right? So I'll just go with convex. Sorry, this is fine, man. Convex hull of, I need the parameter points actually, right? So within this function, first we'll be making use of the points dot length, actual length of the points everywhere. So let me assign this one to the variable n here. So I'll just pass here points. Yep. So the next thing is, if value of n is greater than 3, then we have to return this one empty array. Yep, so this is fine. Next, let's move on with the further things. We have to find the bottommost point, right? So I'll just go with min y, minimum y. Let me set this one to the, or let me assign this one to the points of 0, 1 respectively. The next part is min I. Let me assign this one to the 0. Next, let me go with for I in range, for I in range 1 comma n. So what shall I do now? Let me go with a simple if condition. If points of this one I, if points of I1, if it is less than min y, this is fine. Or this one, points of I1 actually, points of I1, if it is equivalent to the min y actually, min y, and points of I0, points of I0, if it is less than points of this one, I'll just go with the min I actually, min I, along with the min I, let me go with the 0. Then what we'll be doing, I'll just assign the min y to this one, points of I1. Yep, points of I as well as 1. Yep. Next, let me assign the min I to the I directly. Yep. So this is fine, I believe. Yep. Easy one. So next, let's do one thing. Let's place the bottommost point at the first position. So first, I'll just go with the points of 0 here, first position, right? So next, let me go with the points of min I, right? So I'll just go with the min I here. Let me pass this one and let me assign this one to the points of min I. So points of 0, let me assign this one to the points of min I here. So this one, and for the points of min I, let me assign this one to the points of 0, right? So this, yep, so this is fine. So we're just placing the bottommost point at first position. Let me go with P0 and let me assign this one to the points of 0, points of 0. Yep, so this is fine. Next step, let's move on with a further step here. Step 4, we have to sort the remaining points based on the polar angle with P0. Polar angle with P0. I'll just go with polar angle. Uh, Let me pass P. So this is fine. Let me return here. What shall we return? I'll just go with math dot. I'll just go with 8 and 2. So this is fine. Mm, P of 1, along with a P of 1, let me go with a P of 0 as well. Let me go with minus P0. uh, Yeah, this is fine. P of 0 minus P0 of 0. Yep, so this is fine. Why this one we are showing P0 is not defined. We have just defined here, right? Points of 0 actually. This comes under the convex hull actually. This is fine. 1 second, just give me a second here. Where is this actually? So we are just going with here P of 1. So this is fine. P of 1 minus P0 of 1. Oh, sorry. So I'll just go with P0 of 1 here. P0 of 1, P of 0 minus P0 of 0. So this one again, this is showing not defined. So do we need to this one? We are going with the helper method polar angle or the function polar angle, right? So this is fine. Within the convex hull, let's do one thing. Sorry, 1 second. Might be an indentation issue. So I'll just go with here. So yeah, this is fine, I believe. Let's check. Yep. So now the error is gone. Let's do one thing. After returning, I'll just come to the points here. Points. Let me assign this one to the P0. This is fine. Less sorted off. I'll just go with the points. I'll just go with the points of this one 1. This is also fine. Let me go with key. Let me assign this one to lambda. This is fine. Let me assign this one to the lambda. Polar angle of P. This is fine. Polar angle of P. And also let me go with this stuff. P0, comma, P0, comma. Yep. So this is fine. So the next step here would be this one. Let's move on with the call point. So this is fine. We have to process the points and maintain the stack, right? So if we remember the this one, what do we call explanation part. So let's do one thing. Let's process the points and maintain the stack directly. So I'll just go with here stack. First, let me call the points here, points of 0 actually. Along with the points of 0, we need points of 1 and points of 2 as well. It's points of 1 and points of 2. Yep, so this is fine. The next part is let's move on with a for loop here. For I in range, what's the range? From 3 to n respectively. So within the for loop, I'll just go with while length of the stack, if it is greater than 1, and let me call the orientation function that we had written earlier actually. I'll just call the stack over here, orientation of stack of -2. So this is fine. And stack of -1. So this is also fine. Finally, I'll just go with the points of I. I'll just go with the points of I. If it is not equal to 2, if it is not equal to 2, then we have to remove the last point if it doesn't make a left turn, right? So that was the last point actually within the explanation part. So I'll just go with a pop here. Yep, so this is fine. The final step is let's append the points of I to the stack actually. So how can I write that one? So I'll just go with here stack dot append. what we need to append, as I've said, I'll just go with points of I. Yep, so this is fine. Finally, all we have to do is we have to return the stack. We have to return stack actually. So this is fine. Next, let's move on with the example input points. Yeah, let's move on with the example input points. Just give me a second here. So let me do one thing. Let me consider that one from the Google. Let me take the example usage from the Google. Just give me a second here. Yep. So let me paste it over here. So these are the input points that we have considered, right? So we have just called the convex cell function. We are just making a function call here. Finally, we are just going with the output print statement just for the interactive purpose, right? So if I run the code, so I have explained the code step by step. We are we should be knowing the algorithm by now. Yeah, let me explain this one again. So here orientation part. So orientation here, this one function whatever we have written, so basically we are checking whether 3 points make a left, right, or straight line. So that's what we are checking here from line number 27 to 31, right? So next, let's move on with the distance, this one function or the dist that we have considered here. So this helps resolve the ties when points have the same angle, right? So this is fine. Next, we have went with a convex hull. Convex hull function, basically we first find the lowest point here, right, which acts as the pivot. Then we are sorting all the this one. What do we call? We are sorting all the other points by polar angle relative to this pivot. This is fine. This we know. Then what we are doing, we start pushing points onto the stack. We have made use of the stack, right? So from the line number 56. Yep. So if a right turn occurs, the last point is removed. We are popping here, right? So yep, we'll continue until all the points are processed, right? So the remaining stack forms the convex hull accordingly with the explanation part, right? Finally, we'll print the final hull points in the order accordingly with the example usage that we are considering here. So this is fine. Let me do one thing. Let me copy this one entirely. I'll just give here Control J. So yep, I'll just give here fine Python followed by the file name.py. So one second. So we are not getting the convex hull points at all, right? So we have to get the output here 003144 and 03. So something in the convex hull function then point n greater than 3. So this one has to be less than 3 and not greater than 3 actually. For less than 3 actually. If it is less than 3, then we have to return this one empty array. So this is fine. If I run this one now, oh my god, what it is saying? Oh, polar angle, this one. Array, I have given comma here. Instead, let me give minus here. So this is fine. Let me give clear screen. So this is fine. Let me, yeah. Now if I hit the enter, see, we are getting the convex hull points on the order 0, 0, 3, 1, 4, 4, and 0, 3 respectively. We are getting the absolute correct output. See, for the output, for the input that we have considered. So let me show you step by step. This one. This is easy, man. Just listen to this carefully. That's it. Yeah. Here we have went with these points. I hope algorithm part is completely clear, right? So whatever we did. So see, here we have considered this input, right? 0, 3, 1, 1, 2, 2, 4, 4, and 0, 0, 1, 2. Same thing, 3, 1, and 3, 3. First of all, 0, 0 is the lowest left, this one, leftmost point, or this one, our pivot actually. 0.0, 0 is our pivot actually, right? It is the lowest leftmost point actually, our pivot. You can just call this one our pivot. So this is fine. The second point here would be 3, 1. So 3, 1. So 3, 1 forms the first edge going upward. First edge going upward. 3, 1 forms the first edge that is going upward, right? So this is fine. The third one is 4, 4. So what does the 4, 4 do here? So this is nothing but the top right extreme point, right? Top right extreme point. So this is fine. The final one here would be 0, 3. So what is 0, 3? 0, 3 completes the outer boundary and closes the hull. Completes the outer boundary and then closes the hull. right? So here the convex hull, this one, what do we call, points in the order has to be 0, 0, 3, 1, 4, 4, and 0, 3. So that's what we are getting here. In simple terms, all inner points like 1, 1, 2, 2, that's present, right? That are inside the hull and it is not part of the boundary. So we'll not be displaying that one in the form of output. So these are the main points or the output basically. Yep. So we have got the desired output here. Let me delete this one. We have got the desired output. Yeah. So now we are done with the convex algorithm. Let me summarize whatever we have learned so far before moving on with the next algorithm actually. We have to remember these 3 to 4 points. This is very important. The first point here would be convex hull is the smallest convex polygon enclosing all the points, right? So this is fine. The second point here would be Graham scan. So we have made use of the Graham scan, right? Graham scan finds it an big O of n log n, right? So Graham scan finds this one an big O of n log n using sorting and stack based reversal. In the main function, convexal main function, we have made use of the Graham scan itself. So this is fine. The third one here, the key geometric operation is determining the orientation or turning the direction, right? So the first itself, we have written the orientation function, if you remember. Yeah, this is one thing. And the final step here would be this one. It is used for this is useful in computer graphics, main thing, pattern recognition, second main thing, GIS systems, third thing, and finally the collision detection, right? So these are some of the points that we need to remember at any cost, right? So this is fine. Now we are done with this particular algorithm, convex hull algorithm. So next we'll be discussing on the topic closest pair of points algorithm. For now, this is it. Thanks for watching, guys.